Welcome, applied calculators. It is time for us to take a look at the derivatives of logarithmic functions. Why would we do such a thing? Well, if you remember what the log function looks like, it looks something like this. And this function is smooth throughout its domain, which means that we can always draw a piece of tangent line, a piece of tangent line. And if we can always draw a piece of tangent line, we can always find the slope of that tangent line. And if we can always find the slope of that tangent line, we can find derivatives of log functions. So let's think about this with respect to the natural log function, which, as a reminder, looks like this. Well, we didn't think about it like this at first. We thought about this, sure, there's a base of e. We thought about this through the lens that e to the y is equal to x, right? This is the inverse of y equals e to the x. And the inverse of y equals e to the x is x equals e to the y. Now, our last lesson taught us how to take derivatives of the exponential function, so we can take the derivative of e to the y, right? The derivative of e to the y is e to the y times dy dx. That's the chain rule, right? The derivative of e to the x is e to the x. The derivative of e to the y is e to the y times dy dx. And the derivative of x is 1. So dy dx is 1 over e to the y. Now, that's not helpful because this is a function in terms of x, and this is a function in terms of y. Lucky for us, e to the y is x, and so the derivative of the natural log function is 1 over x. The derivative of the natural log function is 1 over x. That is a huge, huge piece to know. The derivative of the log function is 1 over x. And the only log function we talk about is the natural log function. There are other log functions we don't much care because their derivatives are not nearly as nice. So find f prime of x if f of x is the natural log of e to the x plus 1. I'm going to do this question for two reasons. One, it's going to remind us about the chain rule, because this is basically a chicken nugget. And the other will be clear in a moment. How do we find f prime? Well, the derivative of the natural log of something is 1 over something, right? But this is a chicken nugget, and so the chain rule applies. The derivative of the natural log of something is 1 over that something times the derivative of the inside. And this harkens us back to the lesson we did last time, where the derivative of e to the x is e to the x, and the derivative of 1 is 0. So you could simplify, make it one big fraction, but you don't have to. What's the other reason I wanted to talk about this? Because it is not true that the natural log of e to the x plus 1 is the natural log of e to the x plus the natural log of 1. That's not true. Natural log doesn't distribute through parentheses. That's a no-go. Now, if you knew that there was some natural log of e to the x somewhere, you would remember that that's x, and the natural log of 1 is 0. It would be great sometimes to be able to distribute a natural log and get a much simpler expression, but that's not how things work. We don't have a rule about a log of a sum. We've got rules about logs of products and rules about logs of quotients, but no rule about logs of sums or differences. Let's find g prime of x if g of x is the natural log of x squared plus 3. Take a moment, hit the pause button, give it a go, see what pops up. Okay. How do we take the derivative of the natural log of something? It's 1 over that something times the derivative of the something. 1 over the thing times the derivative of the thing. And you could make it one big fraction. That would be just fine. If I asked for the equation of a tangent line, you could find it because this thing is the slope of the tangent line. All of the things that we used to do with derivatives can now be done with derivatives of log functions. I will throw in, because I should, what about logs in other bases? What do we do with those? Well, the log in the other base is the same as the natural log x divided by the natural log of b. This is called the change of base formula from Algebra 2. You can take a log in any base and turn it into a log that we like. Why do we like this? Because we know what the derivative of this is. The derivative of the natural log of x is 1 over x. And there's this number. This is a number. B is a number, so its natural log is a number. And the way this is normally written is 1 over x times ln of b. Now, why do I care about that? Well, I care about that because now we can find the derivative of exponential functions that are not e to the x, right? We can find the derivative of 3 to the x or 2 to the x or 5 to the x. Why? Because if this is true, then the natural log of y is x times the natural log of b. That's the power rule here. And we can take the derivative of the natural log of y. The derivative of the natural log of y is 1 over y dy dx. That's chain rule. Natural log b is a number, and the derivative of a number times x is just that number. So dy dx in this case is y times ln b. But what was y? It was b to the x. So the derivative of 3 to the x is 3 to the x times ln 3, and the derivative of 5 to the x is 5 to the x times ln of 5, and the derivative of 10 to the x is 10 to the x times ln of 10, and the derivative of e to the x is e to the x times ln of e, but that's 1. So the derivative of e to the x is e to the x. And we can play with those a little while, but I think you've got the hang of it. Okay? Okay, there's another video coming up to talk about logarithmic differentiation because that is something you are going to want to know. And that's all she wrote. Okay, thanks.